Okay, so I will do the first part. So 10.3.1. So if you have a strongly tamed strict SB orbifold with ends or horseback, these type of ends satisfying IE and NA, and then these are smooth and strictly convex. So then it has to be relatively hyperbolic with respect to this end fundamental group. Okay. And uh, and if you have some hyperbolic ends, you can remove that, and then it will still be hyperbolic, relatively hyperbolic with respect to that. So the relative hyperbolicity is going to be proved here, and so first of all, we will actually collapse everything like this to for the concave neighborhood point, and then any these things to a point. So this is some new topology of the boundary. And so 6.3.1, these are mutually disjoint balls. And if you look at this collection, um, then and then you look at all these for each cross set, the union of the sets, the meeting these J is also closed. Okay, so there you need to do some sort of geometric argument, and then by strictly convexity you can show this. Okay, so then you take the quotient. So we collapse each of these, anything in here, this collection, and then you obtain that this is still a metrizable space. So, okay, so that's the we prove later. So that's what you call the compactum. So you need that, and so I will use a theorem of Yaman that is relatively hyperbolic with respect to this. So if you have these three conditions will satisfy. So the first one is, so it acts on the any distinct triple here, then it acts on the properly discontinuous on this metric space. So this is a metric space, okay? So if not, then you can take a sequence of non-degenerate triples and which converge to this triple, and so that these pi are the image of some gamma I, which are mutually disjoint sequences. Okay. So visually distinct, and then these are also these classes visually distinct. Um, so that will show the proper discontinuity for the metric spaces. So by multiplying by some bounded element, you can always show that these will fix these points. So these are some bounded elements. So these will no longer preserve omega I omega, but you can see that now it's represented for this plane containing this is represented by some diagonal matrix like this. We're satisfying this property, and so you can consider the case when some of these are going to infinity and something going to zero, because if it's all bounded, then of course this means that these both of these sequences being bounded means that the gamma I is also bounded, and that's we show that these are infinite mutually distinct. Okay, so uh, uh, so right. So if these both are bounded, then the pi will be uniformly, these will be uniformly bounded, and then so so again I showed that this very contradict the strict convexity, and right right. So that's how I will do it. So some of these has to go to infinity and zero, and uh, So by strict convexity, and we collapsed all these. Uh, so now we consider this, or this is bounded. Okay, then suppose not, then these are going to infinity. Okay. So I mean, so we assume this to be true, and then the thing is that if this thing, these kind of things are holding, I mean, these kind of things are holding, then I show that these uh, if this holds, and these are bounded. So if not, then they will all go to infinity, and you can choose some generic argument element meeting these endpoints, and then again you can show it destroys the proper convexity. So if these are bounded, then the sequence of segments converges to this, and then the PQ must be in the boundary here. Okay, so because there's some limiting argument, so this will contradict the strict convexity. Okay, so again, if you so this is bounded, you again the contradiction. So this means that you cannot have these kind of sequences. So therefore, it means that it's properly acts properly discontinuously. Okay. Okay. So then, so for the second part of the Yaman's work, then using the Yaman's work. So for each group, for a fixed point, this is about for the bounded parabolic group in the sense of this. So X is corresponding to the end. Then you saw that there was this homeomorphism to the boundary, so therefore these parabolic fixed points, so they are the parabolic fixed points. I mean parabolic subgroups. So this works. And then for three, we know that we show that any point that's not horospherical or lens-shaped, or these type of fixed points, then I show that this is a conical limit point. So then this will complete the proof by this theorem. So if it's to show its conical limit point, we need to find the sequence of transformation and then distinct point A, B, so that these P and Q will converge to A, B. So the point is this has to be distinct. Okay, so for any point here. So to do that, we just draw some line from fundamental domain to the P, and then as L t goes to infinity, L t goes to P, and then the other endpoint is in a distinct equivalence plus from P. So you can assume that, and then um, because it passes some interior point here. And so you can eventually find some sequence so that LTI is not in any of the Pn neighborhoods. Okay, and then P prime is the other endpoint of the complete extension here. Because if you remove this endpoint, the quotient is compact, so you can find the fundamental domain here, and so you can find some GI so that these TIs are in GI for this fundamental domain. So you find the pullback sequences, and these gamma I's are unbounded. And then you choose this A star to be the attracting fixed points of this. So gamma I, you can choose this convergence subsequence that converges to some element here. So you can attracting fixed point attracting points of the sequence is this, and then the repelling ones are the null space. So if you remove anything in the null, then it converges to A star locally uniformly by the linear algebra. So, since this is a convex subset, this is also a convex subset. So they should be in the collapse subset because of the strict convexity. So they should always be. So as long as this is not in here, and then this is bounded away from the gamma t. So this accumulates only to A star. So therefore, this P has to be in this null space, and so whole thing has to accumulate only to A star. So this is not what we have. So this means that P has to be in here, and then by strict convexity, this always has to be in P. And so for any other point, you always show the local uniform convergence using the A star. Okay. Because these all converge to this linear transformation. And so we show so then we can show these are really the what converge to A and B, which are different. Okay, so that's the argument. Okay, so we found these sequence. So because it doesn't degenerate to anything like a point. Okay, so that's the point here. Okay, so next we'll need this root-2 theorem. So if you have some thing like this, and the pi 1 to pi m is an n fundamental group, so which is hyperbolic. So if it's relative hyperbolic with this, if and only if you remove some hyperbolic ones. Okay, so that's still okay. So the basically that you have to consider their paper, and then so you look at their notion of asymptotic tree-graded method, and then this condition isn't really changed when you add or drop these conditions. Okay, so that's the thing, and then I want to do the converse of this. So to prove the converse, I have to shape off every lens shape Rn, and then we need to expand the total geodesic ideal boundary component by lens enabled, and so then we take the interior outside of these lens to obtain omega 3 O3, and then so you remove some horospheric enabled, you call it O4. So then this O4 is actually quasi-isometric with the fundamental group itself. So that's because so once you do this kind of thing, you realize this will be the quotient will be compact orbifold, so it has a compact fundamental domain and so on. So that by the by the fact that it has compact fundamental domain, you can get the estimate to this quasi-isometry. And then theorem 10.3.4 is that if it satisfies I and NA, and it's smooth and strictly. So if it's relatively hyperbolic with respect to N group, then it's actually strictly SPC. Okay, so the strictness will happen. So that's the converse. And so the basic proof is if you suppose it's not strictly convex, then there's some segments here, and then these so you make this into a maximal segment, which is not intersecting in the lens ones and so on, and so then basically we so this L0 you draw these two segments. So these are maxima, and then S1, S2 inside the omega, and then this will be a triangle, and then you can find the sequence of points converging to on this triangle, which converges to point X in L0. And these distances are going to infinity in the Hilbert metric. So the basic idea is that so you use a maximality of L, because if it's not doesn't happen, then you can show its maximality is verified, not true. Okay. Okay, so once I have that, then this xi, of course, is not in these any of the n neighborhoods, p n neighborhoods. You can choose that because if it's in there, then I mean these L is not in any of these n neighborhoods. It's not a subset of single one, so you have to argue like that, and so that's some difficult part here, and then you want to choose GI so that this XI is sent to fundamental domain or 4, I think, and then you keep showing that then this triangle will converge to non-degenerate triangle passing some point of F. Okay, and then but the next lemma shows that this limit has to be in the some boundary has to be in the generalized N shape Rn, so S of this BE, or so that's the only possibility. But then this means that it is in the some Pn neighborhood, and so some sort of N neighborhood will contain this, and but GI goes to T infinity, but we said these always pass some fundamental domain outside the this UI. So this gives you a contradiction. Okay, right. So the key point will be this lemma here. And next, if it's not C1, then again then you take the duality and then you do the similar thing. So now we'll go to lemma 10.3.5. So this is considering the regular hexagon is a hexagon with interior, the triangle with geodesic edges parallel to the side of unit norm, and all the edge lengths is being 1. So this has a hex matrix, so you can consider these kind of hexagons, which are the some increase blow up, so some size increase of some unit regular bore, regular norm, unit norm bore. And so the proof of this being inside this is that so you have any triangle like this, then 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 you can find these horribles, and then you show that these horrible can meet only in some sort of bounded sets, because if not, then this will give you some contradiction again. So the only thing is, so then if it intersects with horrible in a bounded neighbor, you can remove all these by making the horrible spherical end neighbor smaller. Okay, so that's the argument. And then the point next is that so this then this, if it's relatively hyperbolic with respect to this, then the asymptotic cone is of this is asymptotic tree graded with respect to these kind of cosets, and so the pi O will again be asymptotically tree graded, and so if you look at this regular hexagon in T0, then there's some number, so that if it's bigger than this number, then it has to be in the neighborhood of these ends. Okay, and so these are essentially just the end here. So if you can choose this family, so you can choose this family that satisfy this condition, and so it has to. So these arguments show the boundary of this T must be in here. Okay, so that's the basic argument. And, so again, this uses Drutu's argument here, so on. Okay, so that's the brief summary, and then so these are so the corollary is that if you have a strongly tame S species orbifold with these N, and then so these are hyperbolic. So if this is empty, then it's relative hyperbolic with respect to N group, if and only if this is respect to E1 to En. Okay, so finally, the topological result is that if you have a compact metrizable space and CX is a countable union mutually disjoint compact ends, and the collection has this property is closed. So any the set which intersect this K, you take the union is also closed. In the, it will be closed. Okay. So and then we define the quotient space. So by relation, if it's in the same element, then this is actually going to be metrizable. So so to prove that, you show this is Hausdorff and second countable, and then regular. So use unison metrization theorem. So the basic proof is that
So the basic proof is that you have to show it's Hausdorff and second countable and it's also regular. So to show Hausdorff, you have to remove from some open sets the sets that meets these collection of the sets that meets with itself, and that way you can find the disjoint neighborhood, and also the second countability. You choose L to be in the some countable sets, and it will work. And then of course for the regularity, so for any compact set and the disjoint element, you find the disjoint neighborhood, and then you have to remove anything that C meets with itself, these things. Okay, C meets with these open sets, so you have to remove these.